Happy to talk with you, or at least start off the presentation here for Objective2. Good to see you all. What a good group, what a good team. Good to see you all. I'm Tyson Ochsner from Oklahoma State University. Hope to meet you if I haven't had the chance to meet you yet. Objective2 is focused on how can we develop effective tactical management approaches. So those sort of like in-season, short-term kind of adjustments to the conditions that farmers face as the season unfolds. And so we'll take a team approach on the presentation here. And I'll start off just to say a little bit about the Chronos sites that Andres' group and our group have been working on. And so here's a photo of one of the Chrono Stations out in the field. If you haven't gotten to see them firsthand yet, the idea is that you have an integrated soil, plant, atmosphere monitoring all in one package. Nothing's in the ground. Everything can be picked up and moved at really a moment's notice. So that Romulo's group doesn't break on wood. No, it's for the farmers. So inside this box, where you see the green dot there, if you're in the room, you can see that's the neutron detector. That's what allows us to monitor the soil moisture conditions. Up here is a downward facing digital camera. That's what allows us to monitor the crop development. And then we use Andres's Canopeo algorithm to translate that into a quantitative measure of canopy cover. And this is an all-in-one weather station up on the top that records your sort of traditional meteorological variables. Also records lightning strikes and distance to lightning, which is kind of cool. And all run off a little solar panel and 12-volt battery. So those are what the stations look like. This is sort of generation one of the stations, and part of the goal is to drive down the cost. So if we just talk sort of rough figures, this is like a $20,000 instrument. So the generation two, which we're working to get fully operational right now, they're all built, but we're facing some little challenges. So the goal there is that the generation two cost be down closer to about $10,000 per instrument. And if we can kind of keep pushing the technology barriers that we face, we hope to get generation three down to $5,000. So we'll see. I don't know if we can do it or not. It's going to take a lot of people pitching in and people smarter than me. But we're making progress on that. So generation two, I think Andres has some in the field now. Ours are still in the lab waiting to be deployed. And this is where they're located. So you can see the map here, and now we'll really test the technology. We're going to see if we can take a little tour with Google Earth. I don't know if it'll work or not. So you can see 3 sites in Oklahoma, 2-ish in Kansas. Actually, there's more than 2 now because Andres has been putting out more. So 4 deployed. So we just wanted to show you what these fields look like. Several of these fields, but not all. There's a close match between these Chrono sites and the farmer-to-farmer network, but not exact one-to-one match. So, so if we go to the first field down, well, we'll go south to north. So this is down in southwest Oklahoma. This is one of our cooperators' fields, and just a couple things to note here about this field. This field was in winter wheat last growing season. We had 5 stations in winter wheat last growing season. We collected a really nice, I hope, really nice complete data set for winter wheat last season. And so this was one of those. This is station number 2, and there's the location in the field. And you can see, obviously, it's a terraced field, and this field was actually grazed last year during our data collection. In addition to the Chronos data that we've collected here, we had a student, one of the REU students, Maddie Morris. She went and she did, her and Cole did transect measurements to assess the soil structural quality, soil physical characteristics in these cropland sites and the closest adjacent non-cropland site. So basically cultivated and uncultivated land. This was winter wheat This is like Bermuda grass pasture primarily. Okay, and you'll see these markers on each of the slides. So we've got a poster on that to show next door. So that's site number 2. Then we go back to site number 1, which was, it's on an OSU research station in Chickasha. This is Dr. Arnell's, Brian's field here, which he calls Congo because that's Congo Creek. And you can see the location of the Chrono Station. We'll be deploying another station over here for the 2nd generation. And then you can see the transect there went in the cropland and then over into the riparian forest, which was the native vegetation there. Then we go up to north. Now we're almost to Kansas. This is up by Bremen, Oklahoma. And again, you can see here the location of the Chrono Station number OK003. In this field, also some terraces here. You can see the difference in soil color just looking at this slide of that first one we started at. And then you see the transect where we measured the soil physical properties and then measurements again in this little remnant of riparian forest here. That's near the Kaskaskia River. We go up into Kansas now, and so this one is at the Flickner farm, correct? This is the Flickner farm, one of our cooperators, and now no more terraces, nice flat cropland there. This was also in winter wheat last year during this data collection. We couldn't do the transect, the thing here. Look, there's no uncultivated land anywhere around it, so that was a challenge.
The other Chrono is south of that, so they're
okay, so a pair.
just right south.
Okay, so let me zoom out a little bit. Maybe we'll see it. I don't know if it's on the map.
Yeah, right there.
Okay, so right here will be the second one. Good. So these, yeah, the general strategies, we're going to deploy these in pairs. Oh yeah, there. So, and then up at the Konza Prairie, we have the Kansas Station number 1 located here in the center. And this was also a wheat field at the Konza Prairie. And we also had a transect again from the wheat field and into the grassland there. So I think that's what I wanted to show you about the Chronos.
You might mention that last site that's also neon.
Yeah, right. It's also associated with the NEON, National Ecological Observatory Network site there at the Konza Prairie. So that's a cool link we have there. So that's kind of what we're doing to collect data. We'll continue to try to grow out that Chronos network with 2nd generation stations going out this year. And hopefully next year we'll aim for a 3rd generation of station, each one using a new, some new technologies as we go along. So Andres, why don't you come and say something about yield forecasting, if you would.
Hey, Tyson, what's the depth that you get to with the cosmic ray?
It's a great question. Jerry asked, what's the depth that we get to? It depends on the soil moisture condition, but there's a parameter called D86, which means the depth at which 86% of the neutrons have explored. And that typically we see it running around 20 centimeters or so. Is that kind of what you're seeing? Something in that range. Can go deeper in drier conditions, but that's typical for what we're seeing. Yeah, go ahead.
So maybe just since we're in the topic, okay, I'm going to say a few things here. So we are also working with a startup company that is a spin-off in nuclear engineering that is based in K-State University. So we are also trying to establish this, public-private partnership while developing this new technology. Okay, so one of the questions that we had is, how do we project soil moisture conditions, but eventually, how do we forecast yield if we want to generate an informed decision? And usually for winter wheat, there is a critical period, late February, early March, where producers have to make the decision of applying fertilizer. I'm sure Romeo has many other possible decisions about maybe applying fungicides and stuff, but it seems to me that application of nitrogen fertilizer late February, early March is a critical timing because that depends on the expected yield of the crop, which may have changed from the initial yield goal at the time of planting. So the idea with the forecasting project here is to look at that time, and the idea is to actually ingest all the Chrono stations. So the idea is that we are collecting these canopy cover, soil moisture, and atmospheric conditions, and we are actually ingesting those into the model. So we know what happened between planting and the current timing decision. We measure that. And then from that point on, we use historical weather scenarios to sort of forecast an ensemble of possible scenarios. Now, I don't know exactly what is the scenario that it will happen, but at least we have a wide range of possible scenarios from previous experiences. So what we did here is we developed a web-based model that is a simple soil water balancing model based on the FAO 56. It's a pretty popular model for both rain-fed and irrigated agriculture. It has few parameters, which is good from one point of view. It also has its limitations. And every time that we talk with Ignacio, he's asking for nitrogen inputs, and the model cannot handle that part. But at least we expect that if, from the point of view of having soil moisture information, at least we can capture the main effect on what is going to be the expected yield. I think that's what we want. We want a probabilistic outcome here and say what is the most probable yield. So we have this web-based tool and where we can actually project different scenarios. And one of the goals with this tool is that it's actually fully reproducible. We can upload the weather and the climate, and we can run the model, and we can export a project that can be run by anyone. And it's all web-based, so that means that there is no installation. So it actually runs in the browser, and that usually comes handy if you're in a federal agency. You have a lot of restrictions to install software. And so one of the things that we wanted to do is to make it free of installation. But it also is responsive. I don't know if I have access. Can I open a browser here? Just I think I showed this in a presentation, but just maybe some. And this is just a. There we go. And actually the test data set is something that was collected by Dr. Lolat, I think he's a PhD. So you can just go there and you can see it in action. And the idea is that let me see if I can enable. So there is a toy data set, something that is there available, but you can actually come here to atmosphere and upload your own climate and your own weather data to run it. And the idea is that this will also be driving for a similar version of this model, the data from the Chronos. So let me just visualize scenarios. Okay. Don't take much time. Okay. So that what it's doing now is actually projecting all the different scenarios, and based on the planting day and the forecast date, is going to create all the different projections. And all the computations are happening in real time in the browser in this machine. There is no server involved or anything like that. And so all, thousands of computations for 20 scenarios are happening right now. And so this is a tool for researchers. This is maybe not a farmer would use, at least in its current state. But the idea is to try to have this, model data fusion approach and try to have something like this that hopefully will be available in the Chronos website once we can sort out all the communication problems that we are actually having now. That's a main issue, cell phone signal. We are having different iterations of the Chronos, and so how do we start merging the data from different versions? And there is a lot that is happening behind and under the hood that we need to resolve. But I think this is a good picture of what we are hoping for at the end of version 3. And this is the soil water balance, but it also has a component for canopy cover. And so soil, plant, atmosphere continuum, that's what we are aiming. So if there is information that is available from a time-lapse camera or from a smartphone, the idea is to ingest that information, correct the model, and let the model go from that point that is a known observation. Maybe there is the possibility to also include remote sensing, but so far we are focusing on in situ from the point of view that, yes, it's a limited spatial domain, but it's accurate. Okay, well, at least it's more accurate than a 250-meter pixel. So anyway, that's what we are trying to head. This is what we have as our north, sort of. Yes, go.
Oh, I was just also talking about exporting it, being able to upload it back in, so it saves all your variables between as well.
Correct. So you can even add the. So I don't know where. Yeah. Let's see if I can. somewhere here. This is a place where you can add even the reference or description. Here you can see the citation of where the data set comes from, and you can actually export the model, and everything will go with the model. The weather data, all the parameters, so when you import the model, everything goes back to us when you saved it, so it's fully reproducible, from the point of view of reproducible research concept. And Paul and I, we've been exchanging, he's been testing the model and showing, sending me things that were not working. And because of this, I was actually able to load the model and replicate exactly the problems he was facing. So if there is a research publication, the entire file can go with a paper as a supplemental material, and then someone can upload this and exactly reproduce the figures that we have. So anyway, that's what I have, and I think Cortez is moving in the same direction. So that's not a PowerPoint.
Yeah, so I guess like our group at Maryland, we're working more with like the process-based modeling. So it's all like Epic and Apex focused. And yeah, my next slide will tie in more closely with sort of like what Andres was presenting, sort of similar type of framework. But I guess kind of like an early step for us was, okay, we're running these models in a region where we're primarily focused on wheat-based systems. So we wanted to make sure that if we're interested in water limited production and responses to rates of fertilizer, that we're handling that reasonably well for our base cases. And so just did some data model integration work to just do some model sensitivity analysis and evaluation and calibration procedures. And mainly just collected some long-term and short-term data sets that had some reasonable end rate experiments to do some site level assessments of the modeled responses to different fertilizer rates, but didn't want to be too hyper-focused and make sure that our simulations were regionally representative. So we wanted to balance that with some county level yield information to make sure that at like a larger scale framework, we're handling things reasonably well. And results were fairly encouraging. Sensitivity analysis indicating like the soil hydraulic parameters were pretty core to the modeling outcomes because there's such tight relationships between nitrogen demand and productivity based on water availability. Yeah, definitely some next steps to scale this out in terms of looking at different summer crops in more detail and trying to flesh out some finer scale management practice databases so we can handle things with higher granularity across sort of county level, like within Kansas and Oklahoma. And then like in terms of actual tactical management tools, sort of working on, I mean, it's sort of similar framework as what Andreas was describing, but sort of from a different perspective. I guess essentially just looking at ingesting sort of near-term weather records from NLDOS, which has about like a 2-day lag period, and then supplementing that with about 2-week forecasts from NOAA GFS, and then using sort of stochastic weather generators that are sort of built into the model based on sort of monthly weather statistics that can be generated from those historic time records. And so here I'm focused mostly on summer plantings of soybeans following a wheat rotation. So the map sort of showing the primary growing areas for those rotational practices in Oklahoma and Kansas. And sort of with some old analyses, we saw that some of the predictiveness in this system is being driven by that initial water content at the time of planting, so that while the weather is going to be driving most of the variance, that initial water point is giving us some predictiveness, which is sort of useful for the forecasting perspective. although we still do see lots of uncertainty. So here we're looking at a hindcast with the GFS. So if we're looking at soybean planting dates ranging from May to July, like what would be the expected outcomes both for the wheat following that earlier harvesting of the crop, and then the soybean, depending on how early or late in the season it's being planted. And then these sort of horizontal bars are showing sort of the averages within those regions as simulated by the model. And so you can sort of understand to some extent how, what type of yield anomaly are you expecting? And then we could try to translate that more clearly into a decision space, but at least this is like a first step to the ride, that type of information. And then I don't know, Prasad has a presentation that's sort of similar looking at the nitrogen management tool, but he's not here. So can he share his
So
screen?
Curtis, yeah, after you're done with the southern view, so after you're done, just stop share and then. you'll
Okay.
share this.
Okay. So Prasad, you can share when you're ready.
Hello. Sorry, I'm a little sick. Can you see the screen?
Mhm.
It's the File Explorer.
Yeah. You see the files.
So you can see the slides.
Just your files, like your.
Oh, okay. I think that's one.
Yeah.
Okay. Sorry, I was not able to be there. Because I'm a little sick. Anyway, so here I'm going to present some slides showing the development of nitrogen recommendation tool for winter wheat production systems. So just as a just to provide the context, one of the goals of the project is to improve the nitrogen use efficiency in the rain-fed systems. And we know that one of the major pathways to improve the nitrogen use efficiency is optimizing in-season nitrogen application, so as to improve the yields and reduce the unnecessary application of the nitrogen. So our objective is to develop a web-based nitrogen recommendation tool that can help farmers in optimizing the in-season nitrogen application. So there are quite a few nitrogen recommendation approaches, which are broadly categorized into static and dynamic adaptive approaches. The recommendations from the static approaches apply for every year, irrespective of the seasonal conditions, particularly weather conditions, whereas dynamic adaptive approaches account for the production environment in a given growing season. So dynamic adaptive approaches are generally considered to be more robust, but as you can see in the table, each approach has strengths and weaknesses. So the decision to choose a particular approach comes down to mainly the tools available, affordability, the level of confidence in a particular approach. So in our case, we choose process-based crop modeling approach, and we are using a EPIC agro-ecosystem model to build this nitrogen recommendation tool. So typically in the winter wheat, there are two nitrogen application practices. One is a single application, either at planting or at early spring. And second is a split application, both at planting and early spring. So our objective is to recommend nitrogen rate in the early spring, depending on the information what farmers have done during the planting. For example, if farmers apply certain amount of nitrogen at the planting, our goal is to prescribe whether additional nitrogen is required in the early spring in order to improve the yields. So just to as an example, just to give a background what we are doing. So here I use the epic simulations that we did for one of the sites at El Reno, Oklahoma. For these simulations, we used 3 distinct years characterized with different weather conditions. And we use 0 kilogram per hectare at planting. And in the early spring, we used total 18 different nitrogen application rates. So as you can see, the figure on the left, the yield simulations, simulated yields for different nitrogen rates for 3 distinct years. As expected, the yields were higher for the wet year, that is 2012 and 13 year, and the nitrogen demand is higher. As you can see, the yields were saturated at the higher nitrogen level, whereas for the dry year, the yields were lower, so was the nitrogen demand. So if we calculate the return to nitrogen, we can determine the optimum nitrogen rate considering the rate that produces highest maximum return. In this case, for wet year, 135 kilogram per hectare, whereas for a dry year, it's 60 kilogram per hectare. The normal year, it's 105 kilogram per hectare. So it looks straightforward and simple because we use the historical years and we have actual weather for whole growing season. But unfortunately, when we do the in-season nitrogen recommendations, we are going to have weather only from planting to the decision time. For the rest of the growing season, it doesn't matter what weather we are going to use, whether it would be weather forecast or historical weather or some sort of stochastic weather, there will be uncertainty in our yield simulations. That uncertainty creates some sort of risk in selecting a particular nitrogen rate. So it's important that we conduct a risk assessment when we do the nitrogen recommendations. For that, we are working with Bob Chambers and other economists in the team. For this exercise, we created 35 different weather ensemble members, and each ensemble member include a combination of weather from 3 different sources, from the planting to the decision time, the near real-time weather, and the next 10-day weather forecast from SubX system, and the rest is weather from one of the historical years. So since we use 35 years historical weather, we have 35 weather ensemble members. Essentially, we ran the simulations using each weather ensemble member for different nitrogen rates, and we got the yield distributions. So the figure on the right shows the yield distributions for different nitrogen rates. And as you can see, the yields increased with the nitrogen rate, but at the same time, the variance also increased, meaning that the risk to select the higher nitrogen rates also increased. For example, if we consider the median return to nitrogen, so the optimum nitrogen rate would be 105 kilogram per hectare, but there is a lot of variance in the return to nitrogen. So under those circumstances, the decision to choose a particular nitrogen rate depends on the risk acceptance level of the farmer. So the economists categorize the farmers into 3 different groups: risk tolerance, risk neutral, and risk averse farmers. Risk tolerance farmers accepts higher variance and select the higher nitrogen rate, whereas risk averse farmers tend to choose the nitrogen rate that produces less variance. So using this rationale, we calculated the criterion function using the mean yields and the standard deviation and the price of the wheat and nitrogen for different nitrogen rate. For here, I'm showing for 2013-14 dry year under 6 different risk levels. The one being the most risk tolerance level, and 6 being the most risk averse level. As you can see, the change in the criterion function for different nitrogen rates and different risk groups. So generally, the nitrogen rate that produces the highest criterion function under particular risk group is generally considered to be the acceptable nitrogen rate by the farmers under that particular group. So according to this table on the right, the most risk tolerance farmers choose 105 kilogram per hectare in the dry year, that is 2013-14. The risk neutral farmers choose 45 kilogram per hectare. If you remember, for the dry year, when we use all the actual weather, the nitrogen rate is optimum nitrogen rate is 60 kilogram per hectare. So this is one of the ways to do the nitrogen recommendations when we have a lot of uncertainty in our the weather forecasts and model simulations. So the key is to reduce the uncertainty in the nitrogen as the yield simulations. So for that, currently we are working to incorporate remote sensing inputs like soil moisture, and also trying to collaborate with some climate scientists to improve to use some improved weather forecasts, which are from the regional circulation models, and also the ones bias corrected and downscaled ones. So as I mentioned, there are other nitrogen recommendation approaches. There are purely remote sensing based approaches. We are trying to intercompare this approach with remote sensing approaches. And also for the analysis so far, we use the constant wheat price, but we know that at the time of forecast, we don't know the wheat price. So we are trying to incorporate the dynamic price change with the yields. For that, we are comparing with the historical the wheat prices and historical yields based on the USDA reports, and try to incorporate that. So one of the other things we are doing is we are trying to improve our spatial data sets. For example, we recently developed winter wheat crop rotations using Markov chain approach, and continue to develop some remote sensing products to incorporate into our modeling framework. So in parallel, we are also developing the web-based system. Just a second, let me go to the. So this is the prototype working version of the web-based nitrogen recommendation tool. So currently our focus is to develop a system that can provide nitrogen recommendations for 2019 and 2020 growing seasons, because we choose the previous years. So because the farmers have the information, what nitrogen they applied and what kind of yields they got, so that it would be helpful to evaluate this tool. So essentially, the user or farmer can navigate to their field using the search bar or zoom level. They can go to a particular field. And then choose a particular field, and we need some information like when the crop is planted. We can, if the farmer doesn't provide the planting date, the application will take the default date in the database, and also the nitrogen level applied at the planting time, and the growing season, and what the rotation under practice, and the price of the wheat, and the price of the nitrogen, and the model can be run. So since we have 35 weather ensembles and 18 different nitrogen rates, it will take around 5-6 minutes. We are trying to reduce the time by implementing parallelly. That work is under progress, but I ran the simulations for the 1 pixel. Here are the simulation results. So we can get the yield distributions and the criterion functions and the optimal nitrogen rate under different risk levels. So we are this is currently working version. It's not up. It's not up and running yet, but it's running locally. The idea is once we have the tool, we work with extension people, extension team members, and interact with farmers and get the feedback. And also this tool will enable to understand the risk behavior of the farmers, what kind of risk they can take, and so on. There are many things we could do with this application. Sorry, I think that's where we are in terms of this nitrogen recommendation tool. I just would like to acknowledge the graduate students, the Xingzai working on the economic analysis with Dr. Bob Chambers, and Prithvi is helping with the web application. So I think that's what I have.
Thanks, Prasad.
Thank you, Prasad.
Okay. In the next 3 minutes, I'd like to give you a brief presentation in terms of where we are in terms of developing a system to simulate the impact of management choices on at farm scale. The main objective is to develop a system to be able to simulate productivity, resource use efficiency, and soil health dynamics using a modeling approach, being able to capture what might be the management impacts on these processes. To accomplish this, we are using the EPICS model, which is a watershed version of the EPIC model, which we have used substantially in this project. The EPICS model is a watershed scale and farm scale model where we can reproduce different types of management, like rotations, grazing, and manure management, and all types of things in just one single model, and tries to capture all the processes that can occur at the farm scale. So that's the main idea. And for this, we have selected some initial treatments to evaluate. And we have selected the continuous wheat system, the dual purpose wheat, but I'm not going to present results on the dual purpose wheat simulations yet. And also corn, the wheat and soybean rotation, and wheat and sorghum in summer. So this has the idea of being able to increase the cropping intensity of the systems to be able to see if we can improve productivity as a whole for the farm scale. And our idea is to analyze yields, what impact may have in water use efficiency, for example, and also if there'll be changes in some of the soil health parameters. If through the model we can capture some of these processes that may be happening in terms of the soil properties. To implement this, we have used data from the farmer-to-farmer network, which is a component of the RAIN project, an important component. And for this, we have selected
5 representative farms. And some of them coincide with the locations that Tyson presented already. 2 locations are in Kansas, 3 are in Oklahoma, and you can see the map on the lower left showing the location of these 5 representative farms. These farms have different properties, but we have a considerable range in terms of annual precipitation, going from 800 millimeters all the way to 1200 millimeters. And also they show also a 5-degree Celsius difference in terms of the annual temperature. Now, 2 of the farms are located on Argydos, Ashland, and Miami. See if I can show you this. Ashland and Miami. 2 other farms at Colwich and Brahman are on Argydos, and the 5th farm at Hollister in southwest Oklahoma is on a vertisol. With that, we have implemented these 5 farms and have started some of the simulations, and I'd like to share with you some results. The graph on the lower right shows the average wheat yields in a short simulation, in recent simulation, where we show the wheat yields of the continuous wheat system and the wheat soybean system. As you can see, they're fairly, they are quite comparable in terms of across the sites, but there are some differences, plus or minus 20% difference between the yields by site. But overall, the average yield for the whole systems averaged about 50 bushels per acre, which is what it was recorded or reported by the counties. Now, let's see what happens when we try to evaluate at the level of productivity, how we can compare systems across sites and managements. So in order to do that, we can convert the yields of the individual crops based on carbon and express the simulations based on carbon yields. So the map on the lower left, on the upper left, shows the comparisons of the cropping systems, the continuous wheat, the wheat soybean rotation, and the wheat sorghum rotation. And you can see as the cropping intensity increases, carbon yields increase as well. And that has some implication on the use of water and the transpiration. And the graph on the lower left show an increasing transpiration efficiency as you increase carbon yields. So that's up to here. We're talking about just productivity. And now let's see what happens on the right side, what may be happening in the soil in terms of how this flow of carbon, when you change by increasing the carbon circulations into the system, by augmenting the carbon input into the soil, you may start changing the amount of carbon in the soil. And the pie charts on the right show the different distribution of the various carbon pools that we have in the model. Don't pay attention too much at the result, but you can see differences in the 3 systems that we are trying to study. And now, what may happen now in terms of the soil physical properties? And the table on the lower part shows some emerging differences in terms of, based on the treatment, in terms of some of the properties, soil physical properties, one being porosity, another one being field capacity, hydraulic conductivity, and also bulk density. The percentages there are the changes with respect to the initial simulations, and they're very tiny. Perhaps those cannot be detectable, but nevertheless shows the how the system in the algorithms capture the changes in carbon. And we know that carbon is a major driver of these processes, and also they may have an impact on some of the physical properties. We are going to pursue these and try to find out more information about these and see if we can corroborate that we are using the system that can be used with field measurements and see to what extent we can complement the work that is being done at the field scale. So in summary, I think the simulation results promise to support the analysis at farm scale of the management impacts on productivity, resource use efficiency, and soil health, and also to be able to contribute with input and output data from the model to formulate the total factor productivity analysis. And with that, I stop and ask you for questions for me or for the rest of the presenters. Thank you.
Questions for the two group?
I have one.
Mhm.
That is that, well, actually, two. But is there, on the decision tool and things like that, gotten feedback from producers as to when they make decisions and how valuable these are? Because I think a lot of this a priori to see how it fits into their decision-making process.
I think that's essential, and as in particular case of this modeling system we're establishing now, we need the feedback from the farmers, but so far we haven't not been connected with them. But that's the idea.
I think the initial was through the extension and Knoxville and Zorbar, and Jason. I remember, but providing some input on those decision points. But yeah, the next stage, right, is to take advantage of that farm network and others.
Very, very important.
Yeah, the other question I have is thinking about the nitrogen management tool and things like that. What's the yield penalty for a wrong decision?
Prasad?
I couldn't hear. Can you?
The question from Jerry was what might be the impact of wrong decisions on yield and also returns as well, right?
Yeah, I don't know. That's why we are developing for the 2019 and 2020 growing seasons, so we can understand the level of uncertainty in our recommendations, and we try to improve it, and we try to reduce the uncertainties in our tool. But of course, there always be some uncertainty. That's why we are doing this risk assessment. What is the risk level that farmer can, what is the risk levels of the different farmers? And so, I mean, if the uncertainty towards the lower nitrogen rates, that would be higher impact compared to the higher nitrogen rates, but there would be loss of the nitrogen. So yeah, that's why we are trying to develop for the previous years. So that will give us opportunity to reduce the uncertainties in our system before we actually get the operational nitrogen recommendation tool. I don't know if I answer.
Yeah, thank you, Prasad. Any other questions? Okay.
All right. So this is a fluid situation. It's 3 o'clock. It was our break now, but we got 2 more presentations. But